So now we will talk about the electromagnetic optics. So now till now we have studied about ray optics and wave optics. But in the wave optics also there are some phenomena it is failed to explain. So for example, polarization is one phenomena which is not explainable in ray optics as well as in wave optics. So that is clearly explained in the case of electromagnetic optics. So James Clerk Maxwell is the scientist who was famous for his work in the electromagnetic optics area. So here he considered that the light travels as electromagnetic waves. So here, instead of considering it as a scalar quantity, the light is considered as a vector. So that will help us in explaining the polarization phenomena. So the wave optics fails to explain the division of light by beam splitter and polarization, but the electromagnetic optics has a wonderful explanation for the same. So it is a vector theory comprising an electric field and magnetic field that vary in time and space. So that means the light is considered as a mutually coupled vector consisting of an electric field and magnetic field. So these two fields are coupled together and it is varying in both space and time. So here the basic concept is that of the electromagnetic waves. So there are two mutually coupled fields, electric field and magnetic field, and the interaction between them will cause the signal to move forward. So here, as we studied in the wave optics, there is a concept of wavelength same as the concept of which is used in the wave optics. So here it shows the electromagnetic spectrum, and we know we are working in the optical frequencies. And here the energy of photon that is measured using the Einstein's equation, that is E is equal to h into f or hc by lambda, where h is the Planck's constant, f is the frequency in hertz, c is the velocity 310⁸ meter per second, and lambda is the wavelength in meter, the wavelength of the photon or electromagnetic radiation. So the basic fundamental idea is about the Maxwell's equation. So this is the there are four equations: Coulomb's law, or the Coulomb's law regarding the electric field intensity and magnetic field intensity, then the Faraday's law and the Ampere's Maxwell's law. So these four laws are there, which is the base of the electromagnetic optics. So if I am considering the medium as a linear homogeneous medium which is non-dispersive, then the Maxwell's equation will reduce to this form. And the wave equations are obtained from the Maxwell's equation, and the wave equations, and from the wave equation we are getting the speed of light also. So here we are representing the wave equation in one-dimensional form. If it is in vector form, it is represented as del square equal to mu e into dou square a by dou t square. So once we solve these things, we will get the different solutions depending upon the boundary conditions. And from here we are getting the velocity of light c is equal to 1 by root of mu epsilon, where mu is the permeability and epsilon is the permittivity. In phase space, it will be mu 0 and epsilon 0, and the velocity comes as 3 × 10⁸ meter per second. So the character of any medium is represented in terms of the relation between the polarization density and magnetization density that are represented as P and M at one hand, and on the other hand it is depending upon the electric field E and magnetic field H. So the relation which shows the connection between these variables is called the constitutive relation. So that is given here as D is equal to epsilon 0 E plus P and H is equal to 1 by mu 0 B minus M. So where P is the polarization and M is the magnetization of the medium. So this will characterize the medium. These two equations will characterize the medium. So now we will come to the polarization phenomena. So light is considered as an electromagnetic wave. The electric field of this wave oscillates perpendicularly to the direction of propagation. So the direction of propagation in which the electric field is oscillating, that is what is deciding the polarization of that signal. The light is called unpolarized if the direction of this electric field is fluctuating in a random manner. So for example, sunlight, halogen lighting, LED spotlights, all those things are having its electric field which is varying in a random direction. So that can be considered as unpolarized light. If the direction is aligned to any particular, if the oscillation is aligned to a particular direction, it is called a polarized light. So laser is an example for a polarized light. So depending upon how the electric field is oriented, that means in which direction it is oriented, the light can be classified as linearly polarized, circularly polarized, or elliptically polarized. So in the linear polarization, the electric field of the light is confined to a single plane. So it will be varying along a single line only. So here in the left side, we can see that it is varying in the x-axis and it will be propagating in the xz plane actually. And in the right side, it is varying along the, if I am looking from the direction of propagation, I can see a line. That means the variation will be happening along the y line and it is propagating in the yz direction, yz plane. So this kind of oscillation of electric field will create a linearly polarized light. Now we will come to the circular polarization. So here the electric field of the light consists of two linear components. If they are perpendicular to each other, that means if they are having a phase difference of pi by 2 and if they are having an equal amplitude, then the resultant polarization will be a circular polarization. So depending upon in which direction it is rotating, it can be considered as left hand circularly polarized or right hand circularly polarized. So here on the left side, I am having two field components. One is in the x direction, one is in the y direction. But there is no phase difference between the two. So it will give rise to a linearly polarized light, which is varying along the, which is at an angle of 45 degree with the x-axis. And the variation will be in the line only. So it can be considered as a linear polarized light. But in the left side, we can see that there is also two electric field components are there. One is in the x component and one is in the y component. But there is a phase difference of pi by 2 between them. So that will create a circularly polarized light. As we can see, the tip of the electric field is traversing a circular fashion. But in the left side, we can see that the tip is traversing a line only. So that is linearly polarized light, and on the right side it is a circularly polarized light. And the last case is the elliptical polarization. So here it results from two different linear combinations actually. So if they are having two different amplitudes, or if they are having a phase difference other than 0 or pi by 2. So here also it is having two field components and they are having no unequal amplitudes. In that case, even if the phase difference is pi by 2, it will produce an elliptical polarized light. But if the phase difference is other than pi by 2 and if they are having equal amplitudes also, it will produce an elliptical polarization. So this is the most general polarization. So circular polarization and linear polarization are special cases of elliptical polarization. So here on the left side, it is showing the circularly polarized light. And if we see the right side, it is the elliptical polarization. So we can observe the difference in which the tip of the resultant electric field is traversing. So on the right side, it is a circle and on the left side, it is an ellipse. Now we will come to another component like polarizer. So the polarizer's function is to select a specific polarization of light. Suppose if I am having a linearly polarized light which is having an intensity I0, then the intensity of the light which is transmitted through an ideal polarizer will be I0 into cos square theta will be the resultant intensity, where theta is the angle between the incident linear polarization and the polarization axis. So if I am having a linearly polarized light and if I am passing it through a polarizer and assume that the polarizer is having a polarization axis which is rotated by an angle theta degree with the polarization of the light coming, then the output intensity will be I0 into cos square theta. So this is what is described in the Malus law. So if we are considering a linear polarizer, it will be looking like this here. So we are having an arbitrarily polarized light on the left side and we are having a polarizer here, and in the right side we are getting polarization only in one direction. So it can be represented by a matrix called Jones matrix. So it is represented as T11, T12, T21, T22. So depending upon depending upon the polarizer, this matrix will be having different values. So here T is equal to 1, 0, 0, 0 is shown for a linearly polarizer. So if I am having A2x and A2y at the input, and if I am multiplying if I am having A1x and A1y at the input, and if I am multiplying the transfer matrix 1, 0, 0, 0 with that input, then I will be getting only one component. Here I will be getting only A1x. So that means it will transform the wave components A1x, A1y into a single wave component A1x, 0 by eliminating the y component. So thereby yielding a wave polarized along the x direction only. So earlier it is having random direction as x and y. Now it is having only one direction in the output actually. So that means the electric field will be vibrating only in the x direction. So that is the function of a polarizer. Now we will come to the another set of components called the wave plates. So the wave plates are made of birefringent materials. Birefringent material means the different polarized light will be experiencing different refractive indices. Such materials are called birefringent materials. So the light it will be having a fast axis and slow axis. So the light polarized along the fast axis will encounter a lower refractive index because they will be moving at a fast rate compared to the slow axis, and that travels through the wave plates at a higher speed, and when compared to the light which is passing through the slow axis, the fast axis will be having a higher speed. So the retardation describes the phase shift between the polarization component projected along the fast axis and the slow axis. So due to the difference in the velocity of the light which is passing through the fast axis and the light passing through the slow axis, there is a phase difference between the two. So this will help us in converting the polarization of a particular signal to a different polarization. Like this, for example, we can change a linearly polarized light into a circularly polarized light, or vice versa. So for example, this system is represented by a matrix. That means the polarizer, this wave plate is represented, function is represented by a matrix 1, 0, 0 e raised to minus j eta. So this eta will represent the angle in which it is rotating. So here I am taking a pi by 2 polarizer, that is the water wave plate. So that means it is rotating by an angle of pi by 2. So if we substitute eta by pi by 2, that will represent a quarter wave plate. So a quarter wave plate will convert a linearly polarized light into a circularly polarized light. Here it is a left circularly polarized light. So that can be verified by substituting the corresponding values in the input and output and transfer matrix. So similarly, if I am using a half-wave retarder, that is the half-wave plate, then I can convert the linearly polarized light into a linearly polarized light, but which is oriented at a different direction. So if I am using a quarter wave plate, then I can convert a linearly polarized light into a left hand circularly polarized light. So all these things can be verified by substituting the corresponding values in this equation. That can be done as a homework. So then comes the polarization rotator. So a polarization rotator is an optical device that rotates the polarization axis of a linearly polarized light beam by an angle of choice. So if I want to rotate the polarization of a particular light incoming, then we can use the polarization rotator. So now we will see the reflection and refraction in terms of polarization. So here it is mainly classified into two types. One is the transverse electric polarization, that is TE polarization, and the transverse magnetic polarization, that is TM polarization. So in TE polarization, the electric field is perpendicular to the plane of incidence, and the magnetic field of the TE polarized light will be aligning to the plane of incidence. So in the transverse magnetic polarization, it is the other way. That means the TM polarized light, the magnetic field will be perpendicular to the plane of incidence, and the electric field will be polarized light will be aligning to the plane of incidence. So here, as we can see, the left side is the TE polarization, and the right side is the TM polarization. So here, as we can see, the x-axis, y-axis is outward from the screen, and z-axis is upward. So as we can see, the electric field E1 is in the y direction. So that means it is perpendicular to the plane of incidence. Here plane of incidence is xz, and electric field is perpendicular to that. That is called TE mode. But in the second case, the electric field is it is placed in the same plane as the xz plane. So that is parallel to the plane of incidence. So this is the main classification of the in terms of polarization. So on applying the boundary conditions, we will be getting, so here we are having the reflected waves and the refracted or transmitted waves. So we are having two different mediums, and at the medium they are splitting into two waves. One is the reflected wave and another one is the transmitted waves, and that is the amount which is reflected or transmitted depends upon the characteristics of the medium, that is what is represented by reflection coefficient and another transmission coefficient. So in both the case, these are calculated here. So the Rx will show the reflection coefficient for the X polarized light or the T polarized light, and the next one, the Ry will give the reflection coefficient in the other polarization. So here in the first case, it is represented in terms of the eta 2, that is the intrinsic impedance of the medium. And in the second section, it is represented in terms of the refractive index of the medium. And Tx and Ty will represent the transmission coefficient of the two polarizations. So here eta is the intrinsic impedance and N is the refractive index of the medium. So here, first we will consider the external reflection of TE polarization. So external reflection will happen when the refractive index of first medium, that means from where the wave is incidenting, is less than the other medium. So that is N1 less than N2. So here, in that case, we will be using the reflection coefficient equation as shown above. So here, and the theta 1 and theta 2 can be find out using the Snell's law. So here we will verify what is the variation of the reflection coefficient with respect to the angle of incidence theta 1. So using Snell's law, we can find out theta 2 and substitute in this equation. So after that, we can see that the reflection coefficient Rx is always real and negative, and corresponding to a phase shift of pi. So since it is negative, it is showing a phase shift of pi. So for the entire region, we are getting a phase shift of pi here. From 0 to 90 degree, we are getting a phase shift of pi. And the reflection coefficient Rx is always increasing. And from theta 1 is equal to 0 to theta 1 is equal to 90 degree. And at theta 1 is equal to 90 degree, it is showing a value of 1 actually. That means the complete reflection. That is the complete reflection happening. Then in the second case, that is the internal reflection of TE polarization. That means internal reflection will happen when N1 is greater than N2. So here is the case which is the, here it will come in the case of optical fiber anode. This is the case which we are considering. So here, if we substitute the same equation, when theta 1 equal to 0, N1 minus N2 divided by N1 plus N2 is the magnitude at theta 1 is equal to 0. And it increases gradually towards the unity. And when the incident angle is equal to the critical angle, then we will get a maximum reflection. So that is what is represented here. As theta is varying from 0 to 90 degree, up to theta c, it is real and positive. And when it hits the, when the angle is equal to the critical angle, then total internal reflection will happen. So the reflection coefficient will be maximum, that is 1. And after that, it will be remaining as 1, and the phase will be varying in a nonlinear fashion. And in the case of external reflection with the TM polarization, here also N1 is less than N2. So we will be using the equation corresponding to that from this one. For the TM polarization we will be using. So if we substitute the different values of theta 1, we can see that at the initial points, the value of reflection coefficient is negative and real, and hence it is showing a phase shift of pi up to theta b, where theta b is equal to the Brewster's angle. So at the Brewster's angle, the reflection will be 0. That means the N1 minus N2 will be equal to N1 minus N2 will be equal to 0. So at that time, the reflection coefficient will be 0. And up to that point, it will be having a non-zero reflection coefficient, which is real and negative. So, but it is gradually decreasing and it will reach 0. Once it reaches the Brewster's angle, the reflection coefficient will again increase, and at 90 degree, it will become equal to the 1. So that is how the theta variation is happening in the case of TM polarization. So now we will talk about the B number, so that we have already talked in the ray optics case. So it is nothing but a number which will represent or which will help us in identifying whether the fiber will act as a single mode or multi-mode for a corresponding wavelength. It will decide how many number of modes can be traversed or can be passed through a fiber, and that is equal to 4v square by pi square plus 2. If v is very large, we can approximate it as 4 by pi square into v square. So if the v number is less than 2.405, it will be single mode. If it is greater than 2.405, it will be multi-mode. So these are the things which we need to understand about the electromagnetic optics. Thank you.